Thank you for joining us to listen to the final lecture on our first chapter on laser physics course. So this would be about the properties of laser beams 1.4, and I will be talking about the different properties of laser light. So basically the monochromaticity, coherence, directionality, and brightness of light sources. And the first of all, I would like to just point out that all of these properties essentially arise from the coherence properties of your light source. So please be noted that really the kind of uniqueness of lasers as light sources, they arise from the fact that they have outstanding coherence properties. So that's the kind of main thing you should know after this lecture. And now let's actually get started. So I will be first talking about the unique properties in general for laser light. So those would be the monochromaticity, coherence, directionality, and brightness of your light source. And I will be going through these terminology forward next in the lecture and tell you what these actually are. So let's start with the monochromaticity. So basically the kind of like a fact that we only have a single color of light emitted from a laser. So light emitted by a laser really consists in a single frequency or wavelength of light. And this is the kind of high school physics and Wikipedia telling us that we should have laser light and only a single frequency is being emitted. Of course, this is an outright lie to us, but at least it's a good starting point to try to understand what happens. So let's look at this figure first and then go forward. So what we are trying to say here is that when we would be having only a single frequency of light emitted from our light source, then we would be really having a time harmonic laser light propagating outwards from the laser. In practice, there's no such light sources that are purely monochromatic, but always they consist of several frequencies being emitted. And this, when we take the Fourier transform, translates to a fact that we actually do not have a delta peak here, but rather like a distribution that we could quantify using for example, full width at half maximum value. And this red line here corresponds to a case that we would have multiple frequencies giving rise to our so-called single frequency laser output. So why this actually happens, that we either have in a way very narrow band line width. This is due to the fact that only light with a given frequency or frequency range exactly matches the laser transition. So basically what we already discovered, basically we do have this 2-level system or 3-level system or 4-level system, and the laser line transition goes from the state 2 into the state 1, and the lasing frequency is given by mu naught E2 minus E1 divided by the Planck constant. Sorry about the parenthesis issues here. So we should of course divide both E2 minus E1 with the Planck constant here. So we have this specific laser transition amplified, so light of other frequencies really do not interfere with the active medium or the gain medium, and basically they do not interfere with the laser transition. So that's the basic main origin for very narrow band line width operation. So we first of all have a specific laser transition to begin with, and of course we can do a lot of tricks with the actual laser cavity design to even improve the coherence or the monochromaticity of our light source. So in real life, of course, like I already told you, no emission is really purely monochromatic, but always spans a range of frequencies around this central frequency or nominal central frequency of mu naught. And this range of frequencies or wavelengths is known as the line width of our light source. So basically, often used way to quantify what is the line width is to use so-called full width half maximum values. So we look at the line width at half at the value where the intensity is half of the peak value, so full width at half maximum. And the full width, of course, is that we go from all the way from here all the way to the other side of the line, and not just from midway to the other side. So the narrower we have the line width, the more monochromatic our light source is. So this is basically how things go. And in an ideal case, of course, we would have a purely monochromatic light source. So basically we would be shining a time harmonic wave out from our laser system, but that's of course never really the case in real life. An important factor that contributes to this quasi-monochromaticity of a laser light is really the fact that we do have a resonator forming the laser, so we have a resonant cavity, and this cavity only allows specific laser oscillations or resonances to emit light. And this is basically what happens in a real laser system, and this is important because now we can really engineer by engineering the cavity, and this is in a kind of like things we can really do in the lab, unlike of controlling how the material transition actually go. So we can here do a lot more in terms of the line width narrowing and line width control that we can often do in terms of changing the atomic properties of our active medium. Of course, we can cool down our system, and that usually helps narrowing the line width. In practice, it's usually the kind of cavity design that matters more. Okay, let's now go to another property, and that would be the coherence. And basically, all of these properties arise from coherence, so please pay attention here, and we will be discussing more about coherence during the discussions, I guess, at the campus. So, coherence as a property refers to a fact that we do have a correlation in the electric field between different points on the wavefront of a field. And there are two different points, or types, that how we can define how these points are being defined. So if the 2 points of interest are spatially separated on the wavefront, we call this coherence spatial coherence, as we speak of, for example, transverse coherence of light. So this is what happens when we are looking at the 2 points that are spatially separated. And this is shown in the figure here. So what happens, we have our emitter, we are interested in the spatial coherence properties. So we would be looking at 2 different points in space in the same wavefront, and we want to look, do these points have a correlation? If they do, then we have spatial coherence with respect to these points. If they do not, then we don't have spatial coherence anymore. And it could be, for example, the case that when we go too far out in terms of angles or of observation, for example, that point 3 there, we no longer have spatial coherence between the point 3 and point 2. So we, in a way, are like outside the coherence area labeled at SC here. And this is the kind of like view from top of the wavefront. So I'm trying to highlight with the kind of like red line here that would be the kind of coherence area. And here from the top view, the coherence area could look like something like this. Within this coherence area, all of these points, all the field values inside these points are coherent. So basically they are correlated. So basically that means that if we know the phase and amplitude, or basically if you know the phase of this point, the phase of field at this point, then we can also calculate and know the phase of the electric field at this point. But when we go outside the coherence area into a point 3, we no longer have the correlation. So basically the phase can be arbitrary between them, and we really lose the coherence in spatial domain. The other possibility for coherence is that now we are looking at 2 points and the electric field values at these 2 different points, and we are at the same wavefront, but now we evaluate those points at different times. And now we speak of temporal coherence or longitudinal coherence, and this is what the kind of second figure is trying to highlight here. So now we could be, for example, just looking at a single point value, and then we would look at the field value at a later time, and then we would be comparing, do we have correlation between the measured field values? And if we are within a temporal coherence window inside the kind of like a tau c time interval difference, then we would have coherence, meaning correlation between the field values. So if we know the field value at this time, then we know the field value of the electric field at all later times until the tau t times in time window is passed. And then when we would be trying to look at the kind of correlation between a point observed after coherence time, then we would not anymore have correlation. So this is basically a kind of classical picture trying to highlight what temporal coherence means. So spatial coherence as a property, it's really essential for performing, for example, interference experiments with lasers. And this is also a kind of like key ingredient when we would be wanting to make bright light sources. More on that later in this lecture. So it's really actually very important property of laser light. So let's consider these 2 points P1 and P2 on the wavefront of an electric field. Like I already explained in the previous slide, if we do have a phase difference between the points of the field, like E at the point P1 and E field at the P2, if this remains constant over all points of P on the wavefront, then the field is said to have perfect spatial coherence. So now this is the kind of like idealized case that if all of these points have correlation, then we have perfectly spatially coherent light source. And of course, this is not the case in reality. We cannot really have this, but at least we can have a close approximation for perfect spatial coherence. So this is kind of like a good thing to keep in mind regarding spatial coherence. And now, and this is perhaps more transparent and more easy to grasp, something about the temporal coherence. So temporal coherence refers to the correlation of the electric field at two different times at the same point. If the phase difference between these two different time interval values for the electric field, so E at time t and E electric field at time t plus tau c, remain constant for all of different time values between 0 to tau c, then the beam is said to be temporally coherent over this time window of tau c. And tau c is called a coherence time. So basically this is trying to be captured. We are trying to show that in this figure. So when we are within the coherence time, tau c window, we have a perfect correlation. And then something magical happens after that, and we are losing the correlation, we are losing the coherence, so we can no longer know what exactly is the phase of the electric field here if we know the phase of the electric field here. And I must warn you here that this picture, although it's used a lot, it's not very quantitative, so to speak. So in reality, if you would really want to quantitatively understand temporal coherence properties of your light, you would really need to go into a statistical treatment so that the mathematical treatment to really quantify coherence effects in general and temporal coherence is not the easiest of mathematical approaches and methodologies, but at least this simplistic picture tells you roughly where you want to go and how to get started. But of course, the full mathematical treatment is actually quite complicated. If phase correlation holds for all values of tau c, no matter how large is that, how long is that, and even letting tau c, the coherence time, to go to infinity, in that case, we would have a perfect temporal coherent light source. So basically a perfectly time harmonic sinusoidal oscillation would be the kind of like lasing output or like our field of light. So this is the kind of like mathematically like idealized situation so that we would be able to describe our laser source by just using a simple time harmonic oscillation. That's it. In practice, of course, this coherence time tau c is finite, and this is from the fact that the laser is really not perfectly monochromatic. And quantitatively, we can describe this kind of like a fact that the coherence time is finite by just using the uncertainty relation. So basically the tau c, the coherence time, times the line width of my laser, so delta nu, is equal or greater than unity. So this is basically an uncertainty relation relating together the coherence time of my light source and the light source line width. And this is basically the kind of like practical way of understanding how they are connected. If you look at the kind of like example values, what kind of temporal coherence different light sources may have, a wavelength tunable continuous wave high sapphire laser. So they are sometimes used as a kind of like tunable narrow band light sources. The laser line width is of the order of 1 gigahertz. So basically that translates to a fact that the temporal coherence tau c is of the order of 1 nanosecond. It doesn't sound much, but in reality it's actually already quite monochromatic and quite temporally coherent light source. One can do better, so one can have a narrow line width solid state laser, and there usually the line width is of the order of kilohertz, and this is already quite narrow, and then the coherence lifetime is of the order of 1 millisecond. Then one can go really narrow again, really narrow, and we can go using fiber lasers and narrowband fiber lasers, and then we can realize this kind of like of the order of like 10 hertz to 100 hertz laser line widths, due to the fact that we can have very long laser gain medium by making fiber lasers, and that allows us to reach a kind of temporal coherence times of the order of tens to hundreds of milliseconds. And finally, this is pretty much the state-of-the-art ultra narrow line width photonic atomic lasers, where we are approaching this kind of like 1 hertz laser line widths, and that corresponds to coherence times of 1 second. So basically 300,000 kilometers of coherence lengths. So basically we would be able to shoot this kind of laser light all the way into the moon and almost back on Earth, and the laser light would retain its coherence. So that's pretty amazing. And I must say here, I don't know at which is the century you are listening this video, but right now integrated lasers are also progressing pretty quickly and surprisingly quickly towards these kind of like a line widths, so that one is even approaching a possibility that it seems to be becoming a possible to make integrated light sources, so really like cheap scale, millimeter sized light sources that would be approaching this kind of like very ultra line width regime. So in terms of light source development, we seem to be living very interesting times in terms of making integrated lasers and light sources. So extremely interesting times ahead, I think. Now, let's go to a different direction, and now we really speak about the directionality, and this is really connected to the spatial coherence properties of your laser source. So in a way, how monochromaticity is connected to the temporal coherence, then directionality is connected to the spatial coherence of your laser light. And directionality is defined for a light source by a fact. I'm just looking for this figure. Yes. So basically directionality is often defined by this kind of direction angle or diffraction angle theta that gives us a kind of means of estimating how far out we can have the laser light propagate without really expanding too much. And now we speak of a directionality of laser beam, and this really arises from the fact why we have such a directional laser beam light is that we actually do have the laser light formed inside a laser resonator. So basically the kind of like a lasing output light is really almost of a single laser resonator mode, and that gives rise to its very good directionality, basically due to the fact that it has extremely good spatial coherence. Now, laser emission has extremely high spatial coherence, like I said, and this is basically related to the fact that we have a single transverse mode emission that can be realized by a cavity design, and also the size of my beam can be quite large, so that also directly helps improving the spatial coherence. And already I tried to say that the spatial coherence or directionality of light is defined by this kind of divergence angle theta shown in that figure. And the point here with lasers is that the single transverse mode lasers, in case of these lasers, the divergence angle can be made extremely small. So let's go through this by some examples again. So if you look at the simple laser pointers, these are already extremely directional light sources compared to flashlights or LEDs. Usually the beam divergence angle is of the order of 1 milliradian. And if we compare this to an incoherent light source, so for example flashlight back in the days in 80s and 90s, or LEDs these days, the directionality is more of the order of like 10 or 20 milliradians. So we are speaking of an order of magnitude difference in terms of directionality. And then we really go to a kind of like a more proper light sources beyond laser pointers. So for example, the lasers used in a lunar laser ranging experiment, we are speaking of like beam sizes of like 0.5 meter to several meters. The beam divergences can be down to, let's say, 5 microradians. So we are really speaking of exceptional directionality in terms of light sources. And I guess we can really like easily understand this by just making a kind of thought experiment that we would have a kind of like a LED flashlight, and we would try to shoot like a far away object, let's say like a tree in a dark night forest 100 meters away, and we would try to do that with the flashlight. And even if we would have some kind of zoom lens capabilities within that flashlight, we are not able to kind of shoot the one object very far out anymore, like keeping a kind of like beam like properties in our kind of like a ray of light coming through the flashlight. But now if we have a simple laser pointer, then we can already understand, if you have ever toyed around with laser pointers, that they actually do not diverge that quickly, and even like a kind of like a meters, tens of meters, 100s of meters of propagation can be relatively easily achieved using those light sources. So I think you can already kind of intuitively know that there's a fundamental difference in terms of directionality when we move to coherent light sources. So how do we quantify this directionality? Like the radiation pattern that leaves the cavity of a laser resonator, that would be the laser beam, will propagate mainly along a particular direction. And this is, for example, very different from a case that we would have a spherical wave propagating. So we really have a kind of well-defined propagation direction. And subsequently, we will have very small diffraction. So basically the divergence angle will be small. And this tells us that the transverse beam size will only very slowly grow when we are propagating the laser beam. And this we will learn more about in the later chapters when we are going through the ABCD matrix formalism and learning about Gaussian beams. But this is a kind of classical picture showing how a laser beam propagates. So basically it kind of like can focus down to a kind of like a beam waist location, and then it can start diverging back again. And here within this kind of picture, we can see that the divergence angle is being defined as a kind of like value where we are asymptotically reaching the angle when we are going further off in the propagation. But more on this point really later on in our lectures. Don't worry if you don't get this meaning of this picture yet. I just wanted to point you out here that later on we will be learning more about the directionality and connecting these properties of laser light with this property learned already in the first chapter. So lasers, they propagate very nicely. They don't diffract much, or they don't diverge very quickly. And how we can understand this, if you recall the first picture regarding the slides on the directionality. So we can consider a spatially perfectly coherent plane wave hitting an object, an aperture of a finite size of d, shown in that figure 2 slides back. And then what happens is that the diffraction of light causes the wave to broaden in transverse dimensions in the far field. And then after a propagation, we can really approximate that after a propagation of length L, we have a kind of divergence angle of theta approximately that has kind of resulted in a broadened laser beam light, or broadened propagation of light. And this simple reasoning also applies to propagation of laser beams in free space. So we don't even need to be considering any kind of like apertures, but this kind of reasoning applies. And this is based on the fact that we have finite transverse size for the laser beam, and inevitably this laser light undergoes diffraction. And this is basically related to the fact that the position and momentum are conjugate variables with respect to each other. So like a kind of more tighter we focus a laser beam, the more quickly it diverges, and the reverse. So the kind of larger laser beam we have to begin with, the less divergence, less diffraction we will have for the laser light. So the divergence angle theta of our laser beam, it can be approximately written that the theta equals lambda, the laser line width, not line width, but the laser wavelength, divided by pi, divided by the beam waist, W naught. So lambda is the wavelength, W naught is the beam waist, and this is basically a kind of like a good rule of thumb to remember. So that gives the kind of minimum possible divergence angle, and this is known as the diffraction limit. So this really helps out if you can remember this equation in what follows, because that gives you a kind of like very quick and easy means of understanding how laser light propagates. If we have a large beam, So that would mean mathematically that the W naught, the beam waist, would be larger than the wavelength of light. This implies directly that the divergence angle theta would be much smaller than unity, and then the transverse size at a distance of L into far fade roughly becomes that it's a raw value of theta times L. So if you look at that picture a few slides backwards, you see that where this was being derived. And then this pretty much tells us that we have very small, very weak broadening of laser light when it's propagating. Just a word about how to generalize this treatment for a partially coherent beams. Now the divergence angle will be modified that the theta is approximately lambda divided by pi times delta c, and this delta c is the spatial coherence radius of our beam. And this is actually extremely important when we are going into the final property of laser light regarding, so that would be basically the brightness. So we already see that spatial coherence plays an important role in the directionality of laser beams. So in a way, like I already tried to say you in the beginning of this lecture, it's really like all these properties of laser light, they boil down to coherence properties of laser light. So that would be the kind of number one lesson to learn during this lecture. But before we go and talk about brightness, please remember this equation, because I will try to provide an example not shown in the slides regarding the kind of importance of brightness, because it's not maybe the easiest of a kind of property to understand why it matters. So the final important property of lasers, and some people would really say that this is the most important property of lasers, is that they can be very bright light sources. And bright here, it really has a specific engineering meaning. It really has a specific meaning as a terminology. So please follow me in this description. So brightness is really defined as the power emitted by the source per unit surface area per unit solid angle. So this is basically how things look at on a figure. So here we have a power emitted in a given direction by the source per unit surface and per unit solid angle. So this is basically how we are defining brightness. And let's consider a surface element of ds that's shown in that figure, and let's assume that radiation is being emitted into a solid angle of delta omega around some specific direction denoted with z. The power dp emitted along this direction can really then be easily written that the dp equals some term b, and that would be the brightness of the source times cosine of theta times ds times d omega. So this is basically just a kind of like a geometrical argumentation, and here b is defined as the brightness of the source emitting electromagnetic radiation. So this is really how we define by looking at kind of like a definition for the brightness, and here we see this term arising. And next I want to kind of show to you why this actually matters a great deal when we are looking at light sources. So let's assume that we have a Lambertian source. That means that it really emits isotropically in all directions. And recall that for a laser beam, we can approximate that the cosine of theta equals to unity because the divergence angle is small. And we have that the solid angle dou omega is approximately pi times theta squared. Now we can write the brightness as P, the power emitted, divided by pi s, that's the surface area of our beam, times the divergence angle squared. So S is essentially pi times beam waist squared, that's the transverse area of the beam, and divergence angle theta is the lambda over pi times beam waist W naught. Using above equations, the brightness B can simply be written that B equals the power divided by the square of wavelength of light. And importantly, we see here that the brightness doesn't really depend on the beam size as such, but rather it's more like a kind of property of the light source. And now to the final point. why brightness is actually important, although it's not very transparent property of laser light, is that if we would really want to power scale laser light to be as kind of like powerful as possible, so we would really want to make the kind of most powerful or most bright light source out there on Earth. One option, basically, and this is ultimately the only option that you can really power scale lasers, is that you must start using multiple lasers instead of a single laser, because, for example, the thermal management becomes unbearable and so forth. Materials just don't sustain the optical intensities needed to make powerful lasers. So instead of a single laser, you would now, for example, have 10 lasers joined together, or 100 lasers, or 200 lasers even joined together. And now the point is that in order to really also increase the brightness, it's not just enough to glue together 200 lasers and have them emit it, because then you don't have spatial coherence with respect to these 2 or 200 lasers anymore. So basically the brightness does not scale as favorably. And that basically boils down to the fact that you do not have spatial coherence necessarily with respect to those laser beams you're joining together. So you need to have, if you really want to increase the brightness of your laser system, and you want to kind of scale up the power by combining multiple lasers, so you really also must have them somehow coherent with respect to each other, because that's the only way that you can really realize a scheme that you also increase the brightness. So please think about it. I guess we will be discussing more about that on the discussion time on campus, but basically it boils down to this definition for the brightness. And if you recall a few slides backwards, what happened for the spatial coherence when we had a partial spatial coherence, so then the divergence angle increased, and that affects the brightness here. So basically the kind of downside of combining lasers together is that necessarily what happens, unless you take into account and somehow manage the combined lasers to be coherent with respect to each other, you also increase the divergence, and that reduces the beam brightness. So that's the kind of challenge when you are trying to make the most powerful laser systems in the world. And of course, some people are interested in about that, and songs have been written and made on those kind of laser systems. So some people deem this topic extremely important. So now I'm at the end, finally. Sorry for making this too long, but I just wanted to kind of try to clarify to you the basic properties, because ultimately when we are making light sources, when we are making lasers, it's really the properties that matter and not how beautiful and how nicely the physics works, but it's really ultimately the device that matters in the applications. So I will now stop. Thank you for your time and patience, and please stay tuned for the next lectures regarding Chapter 2 on course of laser physics. Thanks, and bye-bye.